In the last lesson, we looked at pedigree charts for looking at autosomal traits. So traits that are carried on chromosomes 1 to 22. We looked at dominant and recessive versions of that. This lesson builds upon that. So as I've said many times before, if you haven't done the last lesson, you need to do that. Or if you're not sure about it, that's fine. Go over that one again, or we can go through it. But this lesson is kind of the most advanced thing that we'll do in terms of pedigree charts. So today we're going to look at particularly X-linked traits. So in the last lesson, we focused on these traits, but I introduced that there are things called sex-linked traits. And these are any traits or conditions that are carried on the sex chromosomes. So on the 23rd pair, that can be on the X chromosome. So females only have X chromosomes, genetic females only have X chromosomes, or they can be carried on the Y chromosome. So males have an X and a Y chromosome. Just looking at these chromosomes in a little bit more detail, as you mentioned, females have two X chromosomes, males have an X and a Y. So X-linked traits are anything that are carried on the X chromosomes. So obviously females or males can have that. Now we do write the alleles with this little superscript because there could be an X or a Y. We need to include that as well as including the allele. Okay, so similar to how we have included alleles for codominant traits and also some of the multi-allelic traits, we use this kind of writing. As I said, these can be found in males and in females, but we've got dominant traits and recessive traits, just like we do with other autosomal traits. For an X-linked dominant trait, so if something has a dominant pattern, females will have that trait or that condition if they're heterozygous, which would be written like this. There's obviously the females will have two X chromosomes. They've got one of the dominant and one of the recessive allele here, or if they're homozygous dominant, so two of those dominant alleles. Males, remember males have one X chromosome and one Y chromosome. So for a dominant trait, males just have to have that one dominant X chromosome and then also their Y chromosome as well. You'll notice up here that the Y chromosome is actually much shorter than the X chromosome. So for any traits or, like I said, conditions that are coded for in this top part of the X chromosome, there's no Y equivalent to that, which means that whatever version a male has in this part of the X chromosome, they will express that trait. Okay? If the trait is recessive, for a female to have the trait or the condition, they need the two recessive alleles. Okay? For males to have the recessive condition, again, they've only got one X chromosome, so they just need one copy of that recessive allele on their X chromosome and then their Y chromosome. So the Y chromosome doesn't have any influence really on these X-linked traits. Because of this, males have higher rates of X-linked recessive conditions, and we'll look at some pedigrees a little bit later. But because a male only needs one copy of the recessive allele to have the trait, whereas females need two. So just statistically, it's more likely that males will just get that one copy than it is that a female will get two of them. As I've mentioned, there's also Y-linked traits. These are only found in males because females don't have a Y chromosome, but we're not going to really look at those in too much detail, but it's just worth knowing that there are also Y-linked traits. All right, the first question is just getting you to interpret some genotypes. I'll go through the first two with you. So in example A, we're looking at a dominant X-linked trait. So it's got that dominant B allele is what will be expressed. So this person has two X chromosomes. So they are female and they've got two versions of that dominant. So you would say they are an affected because the trait is dominant, affected female. Okay, so that's all you need to do for those questions. In B, the trait is recessive. Okay, so again, it's the same genotypes, but now we're looking at a recessive pattern. So this person is still a female, but they have 2 of the dominant allele. So that would be an unaffected female if this trait were recessive. Okay, we're going to look at dominant traits first, and there's a few patterns that you, and rules, I guess, that you can pick up with X-linked dominant inheritance. And in the worksheet, I do want you to kind of explain a couple of these patterns. So if you just have a look at this pedigree, before I put anything up, maybe observe a few things. A couple of things that always kind of come up with dominant traits is that if a child has the trait, so for example, this person is affected, if it's dominant, at least one of their parents must have it. Okay, someone can't have a dominant trait if neither of their parents have it, because where did the dominant allele come from? I'll come back to this top point in a minute. Another pattern with X-linked dominant traits is that if a male has the trait, his daughter must inherit it. Okay, so if we look at, this example here, so this is a male because it's a square, it's shaded in, so they have the trait, and both of his daughters have it. Okay, and that's not by chance. That has to happen, and I'll show you why. Let's say we're using the allele B. Okay, so the possible alleles are the dominant or the recessive, and then obviously there's also a Y chromosome. So for this male here, he's got 1 X chromosome and he has 1 Y chromosome. Okay, so he has the X and the dominant allele because he is affected by the trait, and he also has a Y chromosome. And this is how you would do a Punnett square for this. You put the X in one and the Y in another. Okay, so that is his genotype. For him to have that trait, he has to have the dominant allele, and he has an X and a Y because he's a male. Now, let's assume his partner here doesn't have the, well, we know she doesn't have the trait, so she has to be recessive. Okay, so she is homozygous recessive. Now, if we fill out this Punnett square, so we get the dominant from the male, from the dad, the recessive from the mum. We can also have the recessive from the mum and the Y. Then we can get the dominant from the dad, the recessive from the mum, and then the recessive from the mum and the Y. His daughters will inherit his X chromosome. Okay, daughters will get 1 X chromosome from their mum and 1 from their dad. Okay, so even though the mum handed on her recessive allele, his daughters have to inherit the dominant X allele from the dad. Whereas the sons, you'll see they both end up being recessive because they got the Y chromosome from their dad. The sons can only inherit a Y chromosome from their dad, and that doesn't carry the trait. So they got the Y chromosome from their dad, and then they got the recessive allele from the mum. So the sons are unaffected. Okay, so that is a rule, and I want you to, try and explain it using some of those terms. Another rule or pattern is that a mother who has the trait, so let's say up here, let's look at individual 1, can have children that don't have the trait. Okay, so if you look at her children, she's got 3 kids. These 3 all have the trait, males and females, but there's 2 that don't have it. So again, we can use a Punnett square to show this. So for the dad, we know that the dad here doesn't have the trait. So he's got the recessive and the Y. Now, this can only happen if the mum is heterozygous. Okay, if she was homozygous dominant, all of the children would inherit it. All of her daughters would inherit it. If we go through here, you'll see that in that first example, the son and the daughter would both inherit it, but then she could also pass on that recessive allele, and the dad could pass on a recessive X, so this daughter wouldn't have it, or she could pass on the recessive allele to a son who wouldn't have it. Okay, so another pattern with X-linked dominant traits. Okay, I've put this example in for question 3. I just want you to work through it in pieces. You will obviously have to assign, I think we use the allele A for this one, so it's a dominant pattern. So for example, this is a male here, so he would have the dominant A allele because he is affected, and the Y allele. Okay, if we just looked at this individual, we wouldn't necessarily, we would know that they are recessive. So that person must be recessive. Okay, so recessive individuals, you could figure out what their genotype is. For the affected individuals, they could be homozygous dominant if they're females, or males will have to be have that one dominant allele. All right, looking now at X-linked recessive traits. And again, there are very common patterns that we see in these. If you look at this, you might pick up on a few things. One of the key things is that a child can have a trait or condition if the parents don't. So we've talked about this before, if the parents are carriers. So a good example of that is this individual here has this recessive condition. So they've got the recessive allele in the Y chromosome, but neither of the parents have it. Okay, so that is possible. With dominant, it's not possible for a child to have the condition if the parents don't. With recessive, it is. Another little rule here, if a female has a recessive X-linked trait, her son must inherit it. So we'll go through that one. Let's look at an example. Yep, so this female, she has this recessive trait. So we're going to put her genotype in here, and you'll see that both of her sons have inherited. Remember, this person has married in, so they're not actually her son. Both of her sons have inherited that, even though the dad doesn't have the trait. So the dad here must be, he has the dominant allele, so he doesn't have the trait, and the Y chromosome. So we'll put in his alleles. So if we do, so this is showing, you know, the 4 kids that are possible here. So if we do these 2 first. Now, firstly, both of these individuals would be females. Okay, so they've got the 2 X chromosomes, and neither of these individuals would have the condition because they both got a dominant version and they have to have 2 recessive to have it. Whereas because the mum only has the recessive allele, she has to pass that on to her son because the son only gets the Y allele, the Y chromosome from his dad. This X can't be passed on to a son because if the dad is passing on that X chromosome, we're going to end up with a female. Okay, so if a female is homozygous recessive, she must pass that recessive allele on to her son, and the son will end up having that condition. Another rule is that if a female is a carrier, her sons will have a 50% chance of inheriting the condition. So again, let's look at this individual here. She is a carrier, so she doesn't have the condition. She's got 1 dominant allele and also a recessive. The dad doesn't have the condition, so he's got the dominant allele and the Y. So if we look at all of the child options, so this would be a female that doesn't have the condition. This would also be a female that doesn't have the condition. She'd be a carrier, but she doesn't have the condition. There's a 50% chance that mum will pass on the dominant allele and this son won't have the condition. But there's a 50% chance that she will pass on that recessive allele and her son would have the condition. So there's a 1 in 4 chance of having a boy that has the condition. But if we're just looking at her sons, we're just looking at this line. Okay, so there's 50% chance if we're just looking at sons that they will have the condition. So males, as I kind of mentioned earlier on, males are more affected by X-linked recessive traits than females because they only need one version of the recessive allele to have the trait. A really common example of this is colorblindness or red-green colorblindness. If you have a look at this, if you are seeing all red, you can't see a green number inside that circle, then you may have colorblindness. But this is an X-linked, sorry, that should say recessive. This is an X-linked recessive trait. The alleles we're going to use for this are XB, so that's the dominant version. That person will not have colorblindness. This recessive allele is the allele for colorblindness. Okay, we can see our common patterns here. So, neither of these parents have it, but one of their children does. So it's kind of skipped that generation. Same thing here. Neither of these parents have it, but this child does. If you wanted to figure out some genotypes just from looking at this, we would look at our affected individuals first. So let's look at this person here. They are a male because it's a square, and they have colorblindness, which is recessive. So they've got the recessive allele and the Y chromosome. So all 3 of these people have that same genotype. Okay? Because we know that this individual got their recessive allele from one of the parents, we could figure out where that came from. So this is the dad. Now he doesn't have colorblindness, so his genotype must be that, which means that mum, who also doesn't have colorblindness, so she must have a dominant allele to not be colorblind, but then she also must have a recessive allele because she's passed that on to her son. Okay, these things are quite tricky. This is probably the most complex stuff you will do in Unit 2 biology. So see how you go, have a go at answering those questions. If it's not quite sinking in, that's fine, we can go over it again. But yeah, have a go at question 5 and see how you go. So today we've looked at the alleles and genotypes for X-linked traits, and then we've looked at the different patterns we see in dominant and recessive X-linked traits.